Hello everyone, I'm Fei from Sharcnet. Today I'm going to give you a talk about the deep learning on Sharcnet. And here is a list of my topics today. And there are two major issues. The first one is, what is deep learning? So I give you some basics about the deep learning and tell you the typical models and their computational needs. And the second part is a more important part for my talk is why would I use the GPU cluster? And I will give you some theoretical performance compared with CPU and a GPU. It's not a theoretical performance about the flops or the bandwidth. And I will based on the computational needs and tell you why people use GPU cluster to do the machine learning or deep learning things. And I'll also give you some demos and benchmarks on the most popular machine learning tools. And we're going to solve the real world problem with that tools. And next, I will show you how to build a very deep and large machine learning model on the GPU cluster. And I'll give you some ideas behind the hardware and the software you can need. And I will separate them to two parts. And one is for the intranode communication, and another one is for the internode communication. Okay, let's move on to the first topic. And what is deep learning? Well, you can see deep learning is learning deep. So it's learning. What should we learn here? We are learning the neural networks. So we're learning deep neural networks. That is what deep learning means. And you can see the picture on the top right. It is a single layer perceptron, or you can call it single layer neural networks. That is the neural network we used to have maybe 10 years or 20 years ago. We can only train the single layer neural networks because it's not possible to train the multi-layer perceptron at that time because of the model is not suitable for multi-layers until the restrict Boltzmann machine comes, and we are able to train the multiple layer of restrict Boltzmann machine to make them like a deep restrict Boltzmann machine, or we call the deep belief neural network. After the restrict Boltzmann machine and the deep belief neural network, and our neural network become larger and larger. The deep Boltzmann machine and its variations is a very typical model of deep learning. And there is other kind of deep neural network. We call it convolution neural network. You can see the picture at above, and it is a LeNet 5. It's a very simple convolution neural network which is used to recognize the image. And you can see there are a few layers, two convolutional layers and fully connected layers. So that is another kind of deep neural network we have today. So what is the computational need for restrict Boltzmann machine or for the convolution neural networks? I'm just wondering now, how many of you will close the screen if I start talking about the mathematical magic behind the RBM? But don't worry, I'm not going to do that. For here, I only want to tell you the computational needs for training the restrict Boltzmann machines. So you can imagine here at the picture right, you can imagine we should do something to train the restrict Boltzmann machine. Even you don't know what to do or you don't know how to do. But I'm going to tell you now, the very basic method to train the restrict Boltzmann machine is called the Markov chain Monte Carlo. Every time I hear about the Markov chain Monte Carlo, the first thing comes into my mind is the stochastic sampling. So when talking about the stochastic sampling, actually they are using a Gibbs sampling, but you don't have to know what is Gibbs sampling is. The only thing you should know is the very basic operation behind the stochastic sampling is the random number generation, is the RNG. Then the other things that are important is This is a neural network. You can see that. So we have the input layer and hidden layers. Between the input layer and hidden layers, they are connected with some weight. We call it weight. So the weight is actually a matrix. So every time we want to compute or update the weight, we have to use our input sample to multiply this weight matrix, and then we got something in the hidden layer, and then we use the activation functions like logistic functions or other kind of active neuron to get another result. But we can also train it. We can train it one by one, like one vector multiply the matrix, weight matrix, and we can also compute them in a mini batch. So as we know that each sample we train contribute a little gradient in our gradient descent. So we can train a bunch of them. For example, if we train 100 samples at the same time, so that will contribute an average gradient when we do our gradient descent. What is works very good, and it is quite suitable for the modern hardware architecture, not only for the GPUs but also for CPUs. Then people can update the weights and compute the weights much faster if we use large size of mini batch. And that is restrict Boltzmann machine. And as we can see, we only need the random number generation and our general matrix multiplication. But for CNN, for convolutional neural nets, and it is said that the convolutional layers cost 90 to 95% of training time during the whole training process. To solve the convolutional layers, we have two options. The first one is cuDNN, and the cuDNN is NVIDIA's official library for the deep neural network, so they call it CUDA deep neural network. And for now, it's still under developing, and it can only support a convolutional neural network for now. And another thing is, as we know, if we use the larger kernel in the convolutional operation, it is better to use the FFT to transfer the operations from the spatial domain to the frequency domain. So that's exactly how Facebook do it. So Facebook just open source their convolutional neural network recently, and I read their paper, and they mentioned that if you are using the large kernel, you better use the FFT. And they did some comparison between the CUDA FFT and the cuDNN. So in their model, the CUDA FFT performs much faster than the original convolutional operation in the spatial domains. So other layers are called fully connected layers, but it costs only a small amount of time, so we just ignore this. And we should focus on the convolutional layers here. And I will show you some benchmarks about the random number generation, the matrix multiplication, and the cuDNN, and also the FFT. And all these benchmarks are lead us to a way to GPU, not the CPU. Okay, so why using GPU? The first I mentioned about is the random number generation. As you can see in this slide from NVIDIA, and the CUDA-RAND library runs 70 times faster versus the Intel MKL. As we know that Intel MKL is possibly reached the highest performance on Intel CPU architecture, and it is compared with I think it's a single socket 12-core CPU here. So you can see another example is cuBLAS, and you can use cuBLAS to do the general matrix multiplication, and it can reach 6 times faster compared with the Intel 12-core CPU. And here is the result for the fast Fourier transform, and you can see for most of the signal size, and it reached 50 gigaflops, maybe more performance on this. This is a single precision and double precision on the one-dimensional signal, but it looks the same for the two-dimensional or the three-dimensional fast Fourier transform. And the next slide will show you the benchmark on cuDNN. You can focus on the graph here. So the Caffe is it's a machine learning tool I will introduce you later. Well, in Caffe, the cuDNN can perform 14 times faster than the CPU implementation, and it is compared with the 24-core CPUs. Okay, the first deep learning tools I want to introduce to you is Theano. And Theano is a Python library that allows you to define, optimize, and evaluate a mathematical expression involving the multiple dimensional array efficiently. And it also provides you a transparent use of GPU. It's as easy as just change the define in the configuration files. And the most powerful things, I think, for Theano is their efficient symbolic differentiation computation, and it will compute the gradient for your defined functions. And it will also keep speed and stability in mind and do some optimization on it, so the speed is quite fast. And I will show you a demo and a benchmark. I'm going to use the deep generative stochastic networks as a demo, and I will show you how to run it on Sharcnet machines. And we're going to use it for the MNIST database, which is the handwritten digits. And before I give you the demo, I want to tell you the very basic steps for the learning procedures on Sharcnet. For example, we are on Monk, and we should do very simple modular load Python package. And then we export as a Python path. If you need other packages, Sharcnet Python modular has already included a lot of packages like NumPy, SumPy, other things you need. But if you need more, you can compile yourself and export the path to the system, and the system will find it. And after export the path, you should edit the Theano configuration files under your home folder, and it change the device to GPU rather than CPU. And you can also specify some other flags you want to use. And to run this program is quite simple. You can run it on development node on Monk. Just tap Python and run your Python script. And you can also submit the job to the scheduler to run it on the cluster. Okay, I'll change my screen to the terminals so I can show you how to do it on Monk. So for example, we log into the Monk development node. So I'm going to change my directory to the Theano benchmarking. Okay, here we have. So the first thing you should do is download the dataset. It's a MNIST dataset, and it's quite small, and you can download very fast. And I have already downloaded it. So if you are doing yourself, you have to download the database first. And it's quite easy. So as I said before, we do the modular load. We load the Python modular. It's for our default compiler, Intel. And we got the newest version, 2.7.8. So to run this package, we need another Python package called PLL. So I've already prepared it in my home folder. If you have it, you just export your home folder, and we export the Python path. And after that, we can run it directly because it's in the development node. So it's quite easy. You can download the code on the internet. You can download others, or you can modify others, and you can create your own. So let's check what's happened here. So it will take a little bit of time because the Theano have to compile the binary file first and then do the calculation. So all the calculations are compiled with C, and it can run efficiently. So we need some time here, but okay, as you can see, they're using GPU device 0. That means you're using GPU to do the calculation. Well, just ignore some MPI error because it's not an MPI environment here because it's a single node. Then you can see they're doing the calculation. It's quite simple. Just write the Python code and then you do your computation. Okay, let me change back to the slide and just leave the node there and let it do their computation. Okay, so let me show you the benchmark result I tested. So there are 3 machines that already tested. One is Android with our new card. It's a GTX 750 Ti, and the Monk has 2070. And I also tested on a machine which has a 20-core CPU with the K20 GPUs. And as you can see, I used the Android CPU result as the baseline 1. So on Android, you can see around 7 times faster running on GPU compared with the CPU. And on Monk, I got a similar result. On K20, well, the K20 is more than 15 times faster than Android CPU, and it's also 7 times faster than the 20-core CPU. So that's the reason why people use GPU for Theano. And another deep learning tools I want to introduce to you is called Caffe. Caffe is a deep learning framework developed with the cleanliness, readability, and the speed in mind. So they got a state-of-art speed in all the deep learning tools. And it also included the faster GPU implement with the cuDNN, as I mentioned before, as you can see on the NVIDIA slides. And the cuDNN performs faster than the original Caffe's implementation of convolutional neural nets. And using Caffe, you don't need to code anything. You just modify or edit a text file. Just tell the Caffe how many layers you have, and what's in your layer, how many parameters, how many neurons, just something very simple, and I will show you later. And we're going to do a demo to training, well, CaffeNet or AlexNet. You should know AlexNet because it's quite famous, and CaffeNet is just a little modification to the AlexNet. And we are training it on the ImageNet dataset. So before I show you the demo, and I'll show you basic steps first. And I compiled the Caffe with the GCC compiler, so you have to unload all the Intel-related compiler or pack modulars first, then load the GCC version. I compiled Caffe for 2 versions. One is for Monk, and another one is for Android. because Monk CPU is relatively old. It has only compute capability 2.0. So I have to modify some code to make it work under the large networks, because for some large networks you're running out of blocks. So I mean running out of blocks per grid beam. For Monk GPU, as I can remember, we have only 65K blocks per dimensional of the grid. But for the compute capability 3, and we have around 2 to the power of 32 or something like that. The Caffe, so if you want to run Caffe on Monk, you have to modify the source code. Then you can compile your Caffe by yourself. If you don't know how to modify the code, you just email me and I will show you how to do it. Or you just simply copy my version. But I cannot guarantee the result, because it's not an official modification or official bug fixed. So you have to wait. If you don't rely on my modification, you have to wait for the official fix for this bug. But Android is fine, because Android's GPU has a compute capability 5, so it's much beyond the requirement. And it can also use the cuDNN for acceleration. And I put all the dependencies and the Caffe itself under my work folder. Then you can download them under the work, my name, and my software installs folder. Well, there is a problem for running Caffe on Sharcnet. I'm not quite sure if it is related to the HDI5, but I found that the LMDB database doesn't work very well. But unfortunately, LMDB is the default using by Caffe. So if you want to use Caffe, you have to change the original script from LMDB to the LevelDB. It is quite easy, and I will show you how next. So you should always use the LevelDB for reading and storing your data. There is the disadvantages of LevelDB is that you can only read one database file one time. So if some machine learning model required to access the database file simultaneously by 2 threads. So for that kind of situation, you have to copy your data to make them like a 2 database file, and tell the Caffe to read number 1 and the number 2. After you creating your database file from images, you should modify the training prototypes and tell the Caffe you are using LevelDB to read file. And you should also modify the batch size if your GPU doesn't have a lot of memory. For example, for training the ImageNet on Monk, you can set up a batch size of 256. But on Android, you cannot set up that much larger things. You can only use around 80 mini batch cells. And after you set up all the settings for training and validation, you should modify your solver. And the solver is included the learning rate, the momentum, things like that, and you should also define the max iterations on Caffe. And after that, you just run Caffe train, and then you specify your solver. And I will give you an example for this. Well, it's not an easy example. Well, here we have the result. Well, we got some problems about the coding things, because I think I'm lack of some Python packages here. But the result is right, so you can see this is quite fast. It costs only 40 seconds per iteration. Okay, let me show you the Caffe. we log into the development node, and the first thing we should do is unload Intel MKL and OpenMP. Instead, we load GCC 4.8.2. So we go to the folder where Caffe is. Okay, before we use the Caffe, we should export the path indicating their dependencies. So I'm gonna show you. Well, it's a quite a long path here, and you can see. Well, Caffe used a lot of dependence, like boosts, like OpenCV, like glogs, some other things. And also we export the LD library path as well. Okay, to train the, okay, let's see what's inside the Caffe. Well, to train the ImageNet, you should download the ImageNet image first and put them on data. After that, you can find the examples for the ImageNet training here. So there is a README file and you can read, and I have already created my image by the script. You can see the script create ImageNet.sh. Okay, let's see what's inside it. So this is how Caffe building the database. All things you should do is just modify here. It becomes a level DB, and use another backend. Get another backend equals level DB, and you change all the things. I'm afraid I don't have enough time to do the things, but I've already changed the level DB and create a level DB data file, and you can find it here. To train the CaffeNet or train the AlexNet, you should modify the models. And we go to the models, and we see here, and we can see the AlexNet, we can see the GoogleNet, all the other kinds of things. We open the AlexNet, and then we just modify the training and the validation. As I mentioned you before, there is a backend. We should modify the backend to the level DB. We should also change the batch size, and you can modify the whole neural network, every parameters, every settings, or even you change the layers, you put more layers in it, or you add some drop-off layers. You can do everything just quite easy because you only modify this text file. You don't have to code. And you should also modify the solver. So the solver, in this solver, you can see the base learning rate and the step size and the max iterations, the momentum, and the weight decay. So all the things. To train it is quite easy. You go to the parent folder. So you go to the home folder here. So you just run inbuilt tools Caffe. You train. You give them a solver equals your model. Maybe we use AlexNet. We use AlexNet as example. Okay, they're doing the calculation, and you can check if they are using the GPU. So the first line here, you can see they use GPU with device ID 0. And now it will take a long time to train the AlexNet. Then I just switch back to the slides. Okay, the benchmark result. I didn't test the CPU result because, as you know, the CPU is much slower than GPU. I only compare the different kinds of GPU and give you some suggestion running it. Well, Monk GPU is older than Angel, even if it's a Tesla level, but it's much older. So the performance is really bad, and it will cost us more than 70 seconds to train 40 iters. And for each iterations, I used a 128 mini batch size. That equals we are training 5,000 image. So for this result, that means if we want to train 5,000 image on Monk, and it will cost 70 seconds. But on Angel, it will cost only 50 if you support it with the cuDNN support. And I also test the key 20, and you can achieve a 30 seconds training on the 5,000 images. So you can see it's faster. And if your model is big, and I suggest you to use Monk because Monk has more GPU memory. But if your neural network is small, and I suggest you to use Angel because Angel is faster. Okay, next I want to talk about why do people use a much deeper and much larger neural network than before. As you can see on the top, and it is the Sharcnet I've shown you before. It is used for recognize the handwritten digits. The whole minutes data set include only 60,000 samples, so it's not a big data set. It's very small nowadays. And after that, the people developed the multi-layer neural net, the convolution neural nets like AlexNet. And in AlexNet, they have five convolution layers, and followed by 3 fully connected layers. And for AlexNet, it's training on ImageNet, which has 1 million image in it. Actually, Alex are using more data set to pre-train the neural networks, and it combined the result of 7 convolutional neural networks, and it got a top 5 error of 15%. Well, last year, Google announced their GoogleNet, and as you can see in the bottom is the huge neural networks they're using, and it will achieve a top 5 error of 6.67%. Well, it's double the performance than AlexNet, but the neural network is much more complex. So going deeper is not easy because the Theano and the Caffe supports only single GPU, and it will also took a long time to train on big data set. For example, on AlexNet, if you're using the K40 GPU, which is the best GPU ever, and it takes 26 seconds to train the 5,000 images. If you want to train the whole ImageNet data set for 90 approaches, and you have to spend 160 hours to train the net. For GoogleNet, you need more time because the network is bigger, and they also have to train more approach. So here is the question: is how to train the huge networks in a reasonable time. Okay, let me show you some successful stories about training the huge neural networks. In 2012, Google used the CPU cluster of 1,000 nodes. 16,000 cores in total to train neural networks 1 billion parameters. It is the famous Google Brain project that they used them to recognize the YouTube video frames, and it used the huge neural networks. But in 2013, a research group from Stanford, they're using a GPU cluster with only 64 GPUs, and they can train the same model as Google Brain use. But their model is 10 times larger than these 10 billion parameters. In 2015, just last month, and another search engine company Baidu used a GPU cluster with 144 GPUs to train the network for their ImageNet training. But the difference between their ImageNet or AlexNet is just they use larger image sets. Well, for AlexNet or GoogleNet, they use 256 by 256 image. But Baidu used a 4 times larger image, and they generate more cropped samples, and we can reach a slightly better result. Their top 5 error rate is only around 6%. I think it's the state-of-art result now on ImageNet. They're using only the original ImageNet. They didn't use the unlabeled ImageNet for the pre-trained neural networks. Okay, to develop a deep learning model on GPU cluster, you have to know what the GPU cluster is and what's inside the GPU cluster. So the first I will show you the hardware topology of Monk. So as you can see on the image, well, each black block is a node. In each node, we have a CPU. Actually, it's a 2 CPU socket, but we consider them as CPU. And we have a PCIe switch. Under the PCIe switch, the GPU and the InfiniBand network adapter are connected. And between the nodes, we have the InfiniBand network. And the bandwidth for the InfiniBand network is around 5 gigabytes per second. And for the intranodes, under the PCIe switch, and all the device can achieve around 6 gigabytes per second memory bandwidth. So that's the hardware topology for Monk. And I will go to the intranode communication. Well, within the single node, how do we exchange data between the devices?
We usually have 2 or more GPUs in the node. If we want to transfer data between these GPUs, for example, from 0 to 1, we have to copy the data to host memory first. That means we copy the data from device 0 to host, and then we copy the data from host to device 1. In this situation, all the data go to the CPU memory. If we use GPU direct P2P technology, the data go through PCIe bus directly. All we have to do is malloc the data on different devices and transfer them through a function named CUDA-mem copy peer. I used to help Graham Taylor's research group at the University of Guelph. We implemented multi-GPU Theano for training AlexNet. In this implementation, we use parallel data loading and we implement the data parallelism.
Memory controller on GPU and the CUDA cores on GPU can work simultaneously. That means you can load your data and run the computation at the same time. So when you run the computation, you can load other data. So you can have the latency of data loading. And another things we need here is the data parallelism of AlexNet, where actually we just separate one big mini batch to 2 small mini batch. As I mentioned before, the AlexNet used a mini batch size of 256, but we can compute 2 small mini batch, 2 128 size mini batch on different GPUs and average the gradients they contributed. So for averaging the gradients, we have to use PyCUDA with the GPU direct P2P support. And we achieved a 1.7 speed up with 2 GPUs. And if you are interested in this multi-GPU implementation of Theano, you can find it on GitHub. And I'll show you the link here. So for the internode communication, well, it's more interesting because if your model is becoming larger and larger, it's not enough for you to use only one node with only 2 GPUs. You need 20 GPUs. Maybe you need 200 GPUs. Well, to efficiently use 200 GPUs, you have to know about the internode communication. If you are familiar with the MPI, you know how we transfer data on MPI. If we don't consider the CUDA-aware MPI, this data have to go to the CPU memory and then go to the InfiniBand network, because in MPI send or MPI receive function, only the host memory pointer are accepted if we don't have a CUDA-aware MPI. So that's what we used to do. Before the CUDA-aware MPI, we allocate the memory on GPU for different process, and we copy the memory from GPU to the host, and then we use the InfiniBand network or other kind of network to transfer the data through MPI to other nodes. But nowadays we have a CUDA-aware MPI. So if you're using CUDA-aware MPI, that means the MPI send or MPI receive function can accept the device pointer, device memory pointer. So you just put the device pointer into the function. You can see here in the CUDA malloc, you malloc the memory on different device, and you just send them directly. That's quite easy and simple, and it will achieve a much faster speed because the memory don't need to go to the host memory first, then go back to the InfiniBand. They go from the GPU memory to the InfiniBand buffer memory and then go to other nodes. So it's quite easy to implement a CUDA-aware MPI program. If you have a legacy code, well, for example, your legacy code just transfer the data from CPU process, but the only thing you need to do is you just allocate the memory on the device, and you change the pointer's name from the host name host pointer to the device pointer, and the CUDA-aware MPI will do all the rest of things. But CUDA-aware MPI has its limitations. Well, for example, it doesn't support the MPI reduction. So that means you have to implement MPI reduction by yourself. You can broadcast, you can scatter, but you cannot reduction automatically. So if you want to do the reduction on your data, you have to organize the data from one GPU node, one node to another node, and do the reduction by yourself. But now we have the unified virtual memory here. I think maybe sooner or later the CUDA-aware MPI will support the MPI reduction. So that is almost all for my slide here. So there is only one conclusion I can get here. It's just go deeper on GPU cluster. So at last, I'm going to check the result on our ImageNet training. So you can see here, it goes fine. And it has already passed the 160 iterations. Well, it took a long time, but I will cancel it too. It's just a demo. If you want to try, and you can find all the things under my folder, and I will show you where it is. So, okay, let me go to the folders. So all the things we have here is under my folder. You can see the work and Feynman software installs, and you can copy them to your directory